What we're going to do in part 2 is derive a few more of these sum and difference identities. They're all related to sine of alpha plus beta, and they can all be derived from sine of alpha plus beta. But before we do that, I just want to flash on the screen here. There's this other sheet posted on Canvas, exploring another trig identity, which is all about the sine of the sum identity, and it's just meant to be something to kind of explore a little bit, and I'm just asking you to plug in values. I'm going to flash my solution sheet, which is also posted somewhere on Canvas. It's the point of this sheet is just to help you see that if we're looking at values of sine of a sum of two angles, it's the sine of the sum is always very different from sine of one plus sine of the other, but it always turns out to be the same as this sine x cosine y plus cosine x sine y on the right. And I just think it's interesting to plug in actual values of angles and sines and cosines and see that's true. And in the last line, you have to use a calculator, and you got to do a lot of copying of decimals, and because you're rounding, you might not get exactly the same thing, but it should be very, very, very close. Okay, so let's get back to our business here, and we're going to take this all a little bit further. So we have one identity here, the sine of the sum of two angles. Sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine of beta. Now to take this a little bit further, we're going to observe that sine of alpha minus beta could be thought of as sine of alpha plus a minus beta, of course. So subtraction can be thought of as adding the opposite of the second term. And what I can do is, see, I can plug alpha and minus beta into the right-hand side of the identity up above. So instead of alpha plus beta, I have alpha plus minus beta. If I have minus beta here, I need minus beta in those other positions. So I get sine alpha cosine minus beta plus cosine alpha, copying from what's in the red box, sine of, instead of beta, I write minus beta, because here I have alpha plus minus beta. And I can simplify what I've written down a little bit. I have sine of alpha. Cosine of minus beta is always equal to cosine of beta. That's the even function property of cosine, plus cosine of alpha. Sine of minus beta is always equal to minus sine of beta. That's the odd function property of sine. So this is equal to sine of alpha cosine beta. Now I got a positive times negative, so that's negative cosine alpha sine beta. And so let's sum up what we have here. We have sine of alpha minus beta has its own formula. It's very similar to sine of the sum. Sine alpha cosine beta minus cosine alpha sine beta. So when there's a minus sign here, there's also a minus sign here. This is called the sine of the difference of two angles identity. So it's our second major identity in this section. And what we're going to do now is we're going to work on deriving similar identities for cosine. And they're going to be kind of similar and kind of different, and that's going to be interesting. But first, or I'll say next, we need to verify a few points before we can go further. So I'm gonna break this down into several pieces, and I'm going to number them. Number one, first we're going to show that sine of pi over 2 minus x is equal to cosine x for all x. Okay. Sine of pi over 2 minus x equals cosine x for all x. And so here's how I'm going to do it. And this is like a good little illustration of how we use these identities. I'm going to use the second red box, the sign of the difference identity here, and I'm going to apply it. But instead of having an alpha and a beta, I have a pi over 2 and an x, right? So I just recopy the right-hand side of the identity, replacing alpha with pi over 2, so I have sine pi over 2, and replacing beta with x, right? Sine pi over 2 cosine x, minus cosine alpha becomes cosine pi over 2, sine beta becomes sine x. So I'm just applying that identity with pi over 2 in the role of alpha, x in the role of beta. And see here, now because I have sine pi over 2 and cosine pi over 2 separate, I can actually evaluate them, because sine pi over 2 we know is 1 times cosine x, minus cosine pi over 2 is 0 times sine x. So all I have here is equal to cosine x minus 0, or cosine x, and we just showed what we wanted to show in number 1. Okay, now there are a few steps to this. That's one step. Step 2, I want to show that cosine of x minus pi over 2 is equal to sine x for all x. Okay, so it's a kind of a similar result to number 1, but it has to do with cosine of a difference. And we do this by, I'm going to draw a graph. So I'm taking a different approach from number 1 by drawing a graph of y equals cosine of x minus pi over 2. I'm actually going to graph that transformation of cosine. So let's set up axes. And I'm going to label my usual negative pi over 2, pi over 2, pi, 3 pi over 2, 2 pi. So I'm doing a horizontal shift here, and there's no period change. I'm also just taking values between 1 and negative 1, so there's no amplitude change. And what I'm going to first draw is just the cosine graph, to the parent graph, you might say. So 1, put it in a dotted line kind of way, pi, 3 pi over 2, 2 pi. So that's just y equals good old-fashioned cosine x, no transformation. And now if we want to, let's see, perform this transformation, we have to shift horizontally, right, pi over 2 units to the left, right? So we have to shift, no, to the right, sorry. We have to shift in the positive direction. Shift pi over 2 units to the right. And so what's going to happen? So this point here is going to end up here. This point, by the way, goes there. So I start out the graph like so. This point will shift pi over 2 to here. So again, it's for us, by this point, this should be a pretty easy kind of transformation for us to make. And this point's going to shift over further. And the point at minus pi minus 1 is going to shift over to here. Okay. And I think what you can see is this graph of y equals cosine of x minus pi over 2 is the same as the graph of y equals sine x, right? We're in exactly the standard position for the y equals sine x graph with period 2 pi. Thus, cosine of x minus pi over 2 is equal to sine x for all x. That's what we wanted to show. We've shown point number 2. So we showed this identity, something we haven't called an identity before, or we haven't talked about proving an identity in this way, but we actually proved it graphically by showing that the graphs of the two sides of the equation coincide. They're both just the blue, which is the same as sine x. Okay, so that's step 2. Let's continue on. Okay, so the third point I want to show is show that cosine of x minus pi over 2 is equal to cosine of pi over 2 minus x for all x. Cosine of x minus pi over 2 equals cosine of pi over 2 minus x. The difference here is I've turned around the subtraction of what's inside parentheses. So, you know, we know when you change the direction of subtraction, a minus b, b minus a, normally you get something different, right? So it's maybe a little bit surprising here that we can change the order of the subtraction and we still have both sides of this equation equal to each other. And let's see why. Cosine of x minus pi over 2 is equal to, I'm just going to rearrange. I'm going to rewrite that as cosine of minus pi over 2 plus x. So that's nothing tricky. I just put the negative term first, positive second. And then I'm going to factor out a minus sign from those two terms inside the rounded parentheses. So I get minus pi over 2. If I factor out a minus sign from plus x, I get a minus x, right? So I have a layering of grouping here. This minus, a minus x is equivalent to plus x. And now we know cosine of minus a is equal to cosine a for all x. That's the even property of cosine. Now, the a here that I'm talking about is the expression in the square brackets. So this has to equal cosine of pi over 2 minus x. Well, we're done. We just showed what we wanted to show has to be true for all x. And now, number 4, I'm going to put 2 and 3 together. Put 2 and 3 together to get this is what I want. Cosine of pi over 2 minus x equals sine x for all x. Okay, so let's see, what did we do? Number 2 was, from number 2, we have sine x is equal to cosine of x minus pi over 2. So going from here to here, that equation was our second part of our work we've done here, step 2. In 3, we showed that cosine x minus pi over 2 is equal to cosine of pi over 2 minus x for all x. So now, I guess it doesn't matter which side I write first. We have sine x equals cosine of pi over 2 minus x for all x. I'm just taking the first quantity here, setting it equal to the last quantity there. That's what we wanted to show for part 4. That's what I mean by putting 2 and 3 together. Okay, now we're going to use this fact here. And let's see, we're also going to use one of our earlier results. Let's just go ahead and let me show you where this is headed. So now let's look at cosine of alpha plus beta. So I'm going to try to derive an identity involving cosine of alpha plus beta here. Now, to get started on this, I'm going to think of this alpha plus beta as just a single angle. Just think of that as cosine theta. Cosine theta is equal to sine of pi over 2 minus x. That was our number 1. So I'm coming back to my first page because we kind of forgot about that result. I'm plucking off my result from the first stage of these sub-steps we've gone through. So cosine of theta, or cosine of x, is equal to sine of pi over 2. Here I'll write minus theta for all theta. If alpha plus beta is the theta, this is sine of pi over 2 minus alpha plus beta. I need to put that in grouping. I can distribute that sine of pi over 2 minus alpha minus beta when I distribute. And now I'm going to group again. I'm going to group the first two terms, pi over 2 minus alpha, minus the beta. I'm going to keep that separate. That's equivalent. And this is sine of the difference kind of form. Sine of the difference of two angles. And I've kind of changed my meaning of alpha and beta at this point, but I can apply, going back to an earlier page, the sine of the difference of two angles identity. It's sine of the first, cosine of the second, minus cosine of the first, sine of the second. So what I'm going to get is sine of pi over 2 minus alpha, that's the first. Cosine of the second is cosine beta, minus cosine of pi over 2 minus alpha, sine of beta. So that's like an application of sine of the difference of two angles identity. And now I can work on this even further because sine of pi over 2 minus alpha, somewhere we have that, that's also on my earlier sheet here, that was our number one, is always equal to cosine alpha, or cosine, in this case, cosine alpha, cosine beta, minus cosine of pi over 2 minus alpha. Okay, that was all our work to get to number 4. Instead of pi over 2 minus x, I have pi over 2 minus alpha. So that will be sine of alpha, applying our number 4 result times sine beta. And now I'm going to put it all together. What we're saying is cosine of the sum of two angles, alpha plus beta, that's where we started here, is equal to this last line, cosine alpha, cosine beta, minus sine alpha, sine beta. And this is our identity for the cosine of the sum of two angles, and it is different from the sine formulas because here we're multiplying two cosines in the first term and two sines in the second. We mix up sine and cosine in the sine formulas. Also, what's kind of surprising is we got cosine of a sum here, but we end up with a minus sign in the identity. And so we got just a little bit more to do before we get to some problems. So that was our third identity, third major sum and difference identity. We got one more to do. We want one more. We want to derive cosine of a difference. Okay. And this will be easier, not nearly as involved as the one we just did. So let's see, we're going to think of that as cosine of alpha plus minus beta, kind of like we're going to get the cosine of the difference from cosine of the sum, just like we got sine of the difference from sine of the sum. So I'm going to plug into what we just derived, thinking of this as a sum. Instead of alpha beta, I have alpha minus beta. So it's cosine alpha, cosine minus beta. And I have a minus sign, right? Sine of alpha, sine of minus beta. Now we're going to try to clean this up a little bit. I have cosine alpha. Cosine of minus beta is always equal to just cosine beta. The minus sign gets swallowed because of the even property of cosine. Minus sine alpha. Sine of minus beta is equal to minus sine of beta because of the odd function property of sine. And now a little bit more here. Cosine alpha, cosine beta. Notice that we got a negative times a negative for the second term, so that will be plus sine alpha sine beta. You might have almost guessed that this was coming. So to sum up, cosine alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. Very similar to cosine of the sum. This is our fourth, this is the last of the four major sum and difference identities dealing with sine and cosine. So we're going to stop this video and we're going to actually do some problems now in the next segment.